Lesson: Selecting suitable AI models and algorithms. Selecting suitable AI models and algorithms is a critical step in designing AI solutions, particularly for professionals pursuing the Certified AI Workflow and Automation Specialist certification. The selection process involves understanding the problem domain, data characteristics, and the specific goals of the AI solution. It requires a combination of technical knowledge, practical experience, and the ability to leverage advanced tools and frameworks. By focusing on actionable insights, professionals can effectively navigate this complex landscape and ensure that their AI solutions are robust, scalable, and aligned with business objectives. The first step in selecting an AI model or algorithm is to thoroughly understand the problem domain. This involves identifying the type of problem, be it classification, regression, clustering, or reinforcement learning, and clarifying the desired outcomes. For instance, in a customer segmentation task, the goal might be to categorize customers into distinct groups based on purchasing behavior. Understanding the problem scope allows for the alignment of AI techniques with business needs. Engaging with stakeholders to define clear objectives and constraints is crucial in this phase. Tools such as use case canvases or business model canvases can facilitate this process by providing structured formats to capture the problem requirements and expectations. Once the problem is well defined, the next step is to assess the data. The availability, quality, and characteristics of data significantly influence the choice of model and algorithm. For example, if the dataset is labeled, supervised learning algorithms like decision trees or neural networks might be appropriate. Conversely, for unlabeled data, unsupervised techniques such as k-means clustering or hierarchical clustering could be more suitable. Data exploration and pre-processing are essential components of this phase. Techniques like data visualization, correlation analysis, and feature engineering are critical for uncovering patterns and relationships within the data, which inform model selection. Tools like Python's pandas for data manipulation and Seaborn for visualization are invaluable in this context, allowing professionals to gain insights into the data and prepare it for modeling. With a clear understanding of the problem and data, the focus shifts to selecting the appropriate AI model and algorithm. This involves evaluating different models based on criteria such as accuracy, interpretability, scalability, and computational efficiency. For instance, while deep learning models such as convolutional neural networks are powerful for image recognition tasks, they require significant computational resources and large datasets. In contrast, simpler models like logistic regression may suffice for problems with less complexity and smaller data volumes, providing ease of interpretation and faster deployment. Decision-making frameworks such as the model selection matrix can aid in comparing different models by listing them against defined criteria and scoring their performance in terms of those criteria. Practical tools and frameworks play an essential role in model selection and implementation. TensorFlow and PyTorch, for example, are popular frameworks for building and training neural networks. They offer robust capabilities for handling large-scale data and complex models, with extensive libraries and community support. For classical machine learning algorithms, scikit-learn provides a comprehensive suite of tools for model selection, evaluation, and validation. It includes utilities for cross-validation, hyperparameter tuning, and algorithm benchmarking, which are crucial for optimizing model performance. These tools not only facilitate the technical aspects of model development, but also streamline workflows, enabling professionals to focus on strategic decision-making. Real-world challenges often require balancing multiple objectives, such as accuracy and interpretability. For example, in the healthcare industry, models must not only be accurate, but also interpretable to gain trust from practitioners. In such cases, ensemble methods like random forests or gradient boosting machines can be effective. These methods combine the predictions of multiple models to improve accuracy while maintaining a degree of interpretability. Case studies, such as the use of random forests in predicting patient outcomes based on electronic health records, demonstrate the practical application of ensemble techniques in achieving high performance and interpretability. Another critical consideration in model selection is the deployment environment. Models need to be compatible with the infrastructure where they will be deployed, whether on-premises, in the cloud, or at the edge. For instance, deploying deep learning models on mobile devices may require optimizing models through techniques such as quantization or pruning to reduce their size and computational requirements. Tools like TensorFlow Lite and ONX provide capabilities for converting and optimizing models for deployment in resource-constrained environments. These tools are essential for ensuring that AI solutions are not only effective, but also practical and efficient in real-world settings. The iterative nature of AI model development necessitates a continuous process of evaluation and refinement. Model performance should be assessed using metrics relevant to the problem domain, such as precision, recall, F1 score, or area under the ROC curve for classification tasks. Cross-validation techniques, such as k-fold validation, are crucial for obtaining reliable estimates of model performance and avoiding overfitting. Frameworks like MLflow facilitate the tracking of experiments, model parameters, and results, enabling professionals to systematically refine their models and document the decision-making process. In conclusion, selecting suitable AI models and algorithms is a multifaceted process that requires a deep understanding of the problem domain, data characteristics, and deployment environment. By leveraging practical tools and frameworks, professionals can streamline this process and develop robust AI solutions that meet business objectives. The integration of structured methodologies, such as the model selection matrix, and the use of advanced frameworks like TensorFlow and scikit-learn empowers professionals to make informed decisions and address real-world challenges effectively. Case studies and real-world examples highlight the importance of balancing multiple objectives and optimizing models for deployment, ensuring that AI solutions are not only powerful, but also practical and scalable. Through continuous evaluation and refinement, AI professionals can enhance their proficiency in model selection, ultimately contributing to successful AI solution design.